Hello everybody! In the following video I'm going to talk about the project which I have been working on during the summer. Since this video should stay quite brief, I will only highlight the main points and the main ideas of the project so that you can easily become acquainted with it. Just in the case that you are interested in further details after watching this video, feel free to visit the official Summer of HPC website and have a look into the final report. This project was about the matrix trifactorization. The overall goal was to implement the algorithm in a parallelized manner and improve it as far as possible. While I had been working here at the University of Ljubljana at the Faculty of Mechanical Engineering for 2 months, I have been supervised by Professor Jan Packhaeuser. So let's get started. The matrix trifactorization, as we comprehend it, is a multi-layered matrix decomposition. In order to evaluate this multiple network alignment, you have to decompose the network matrices Ri, which are given simultaneously into the product of 3 matrix factors of lower dimensions. This leads to the following mathematical formulation. It is a constraint minimization problem where the objective function is simply the sum of the errors, and there are non-negativity constraints on G and a symmetry constraint on Si. Of course, the famous Karushkuntaka conditions, also called KKT, have to be mentioned while we are talking about constraint optimization. These are first-order necessary conditions that have to be solved. This looks quite difficult. Therefore, we use the computer to obtain results. Since there are a bunch of methods that we could take into account to solve the KKT conditions, we decided to use a comparably simple method in the beginning. This method is based on a fixed-point approach. Before I could implement it, I had a quick look on my supervisor's notes, where he pointed out how he derived the update rules. Why and how he did that, you will see in the following comic scene. In mathematics, it is often required to put on one's thinking cap. But sometimes even one glance is enough to achieve a solution. After deriving the algorithm, he has already been thinking about a parallel implementation which he delegated to me. If we have a look at the algorithm, we notice that we can definitely parallelize the for loop inside the iteration procedure. Also, it is possible to parallelize the factor needed to update G in each step. Even better, we can just calculate this factor within the same loop. As another approach, we took a second method into account, the projected gradient method. This method works as follows. During each iteration, we move into the direction of the negative gradient, which is the steepest descent, with a certain step length. Afterwards, we project onto the feasible set. Similar to the other method, we can again parallelize the for loop to compute Si. Also, the computation of the step size can be parallelized. Moreover, we can calculate the gradient in the same for loop where the matrices Si are computed. Finally, I can explain how I implemented the algorithms. They were entirely written in C++ utilizing different libraries. Because both algorithms operate mainly on matrices, it was convenient to resort to a linear algebra library. We chose the Eigen library. On the way to enhance the performance, we noticed first improvements when we enabled Blas and Lappach libraries as Eigen backends for both matrix-matrix multiplications and solving systems of linear equations. These backends had a significant impact once we linked it with the Intel math kernel library, because then Eigen silently substituted a few algorithms with calls to Intel MKL routines, which are highly optimized on Intel and compatible processors. It also influenced the performance to the better as we linked Eigen against OpenBLAS, which is a multi-threaded high-performance replacement of BLAS. And last but not least, we used the OpenMP standard to parallelize for loops where it was possible. Now we come to the point where I can show you some results. Let's begin with the content-related results. After each iteration, we could consider a quality measure of the factorization as it is defined on the slide. Accordingly, we investigate the difference in the behavior of convergency for both methods. For this purpose, we generated a simple test case and observed the RSE after each iteration. What you can observe is that the fixed point method converges much slower than the PGM, Here, the green curve indicates the evolution of the RSE for the fixed point method, and the blue curve denotes the evolution for the projected gradient method respectively. On the other hand, we can measure the execution time for increasing dimension of the matrices and compare both methods' performance related with each other. Here we notice that the fixed point method iterates much faster than the projected gradient method. What is actually the aim of the matrix trifactorization? Its area of application can, for example, be found in data science or biology. The aim of the matrix trifactorization is to extract information contained in multi-type relational datasets, for instance, in networks that include both intertype and intratype relationships. More precisely, you can save all the information that is similar among all network matrices into G, and all information that is specifically related to a certain network into the matrix SI.